morning everyone. How are you all? In today's class, we are going to learn about forward and reverse bias in PN junction diode and current flow. So let us try to understand what is a diode. A diode is a basic electronic component used in electronics, which controls the flow of current flow in only one direction and opposes the flow of current in opposite direction. This can be best understood with the example. Like when we charge our mobiles, we use our charger. When we plug our charger in the socket, current flow from socket to the mobile, and it does not flow from mobile to charger. Why? Because of the presence of a diode in the charger, which does not allow the opposite flow of the current. There are diode is made up of two types of semiconductor material, that is P-type semiconductor material and N-type semiconductor material. So now let us try to understand what is a semiconductor. What is a semiconductor? Semiconductor is a material which conducts electricity. Semiconductor is a material that has electrical conductivity between a conductor like copper and an insulator like glass. And what makes this semiconductor so special is that their ability to conduct electricity can be precisely controlled, and they are the foundation of modern electronics, from smartphones to satellites, microchips, processors, LEDs, solar panels, electronic vehicles, diodes, transistors, and integrated circuits. Some common semiconductor materials that we use are silicon. Silicon is the most widely used semiconductor material, and germanium. It is used in early electronics and some specialized devices, and gallium arsenide used in high frequency electronics like smartphones such as like 3G network, 4G network, 5G network, like that, and satellite communication and radar system. These semiconductors, why these semiconductors are so special? Because their electrical conductivity, their electrical behavior can be easily controlled. How? Because by adding some tiny amount of material called doping, and by applying a voltage and by changing the temperature of this material and by exposing them to the light, we can control them. So they are very special. A pure semiconductor like silicon or germanium at room temperature is not a very good conductor. So why? Because it atoms form a crystal that is, and most electrons are tightly bound. However, when we deliberately add some small amount of impurities, a process called doping, the electrical behavior changes dramatically. If we add a pentavalent impurity such as phosphorus to silicon, each impurity atom contributes an extra free electron. This creates an N-type semiconductor where electrons are the majority charge carriers and holes are the minority charge carriers. On the other hand, if you add a trivalent impurity such as boron, we create a P-type impurity, where holes are the majority charge carriers and electrons are the minority charge carriers. Now comes the crucial step, that is the formation of p-n junction. When a p-type semiconductor material and an n-type semiconductor material are joined together to form a single crystal structure, we get a p-n junction. A p-type semiconductor and n-type semiconductor are joined together, we get a p-n junction. It is possible to manufacture a single piece of semiconductor material, either that is germanium or silicon, one half of which is doped by p-type impurity and other half of which is doped by n-type impurity. The plane dividing the two halves or zones is called p-n junction. It should be noted that a useful p-n junction cannot be made by by just connecting a p-type material and an n-type material together, or by the process of welding, etc. Because this would give rise to discontinuities across this crystal structure. During the formation of a p-n junction, something interesting happens at this p-n junction. That is, electrons from the n region, where their concentration is high, begin to diffuse into the p region, where the concentration is low. Similarly, holes in the p region cross the junction. Similar to holes in the p region diffuse into the n region. As electrons and holes cross the junction, they recombine with each other. Here, the electrons move towards the p region and holes move towards the n region. These are the mobile holes and these are the fixed ions. These are called the mobile electrons. This recombination removes the free charge carriers near this junction and creates a thin depletion region that is almost free of mobile charges. And this region is called depletion region. And its weight is about 1 micrometer, that is 10 to the power -6 meter. Because electrons leave the n side near the junction becomes positively charged due to the uncovered donor ions, and the p side near the junction becomes negatively charged due to the uncovered acceptor ions. This separation of charge creates an internal electric field from the n side to the p side. Due to this field, a potential difference is set up across this junction, across this depletion region, known as the barrier potential, or also known as built-in potential. For silicon, this barrier potential is around 0.7 voltage, and for germanium, it is about 0.3 voltage at room temperature of 300 Kelvin. What this built-in potential do? What this built-in potential do here is to stop the further flow of charge carriers across the junction unless supplied by an external electric source. Now let's talk about forward and forward bias. Let's talk about forward bias in AM junction. A PN junction is said to be forward biased when the P type of the material is connected with the positive terminal of the battery and the N type of semiconductor is connected to the negative terminal of the external battery. In this forward biased condition, the external field is applied opposite to the internal electric field of this depletion region. Let's talk about the effect of this forward bias on this depletion region. When this P side is connected to the positive terminal and the holes in this P region are repelled towards this junction, and electrons in this N region are also repelled towards junction. As a result, the breadth of this depletion region decreases and the barrier potential here also will be decreases. And mathematically, this can be expressed as effective barrier potential equal to dB minus V, where dB is the built-in potential and V is the applied forward biased voltage. And this reduction in barrier potential allows charge carriers to cross the junction easily. Now let's see the charge carrier motion and current flowing forward bias. Electrons move from the N region to the P region and holes move from the P region to the N region. These charge carriers recombine near this junction and a large current flows due to this, and large current flows due to this majority charge carriers, and this current is called forward current. And the cut-in voltage for silicon diode is 0.7 voltage, and for germanium it is around 0.3 voltage. Once this cut-in voltage exceeds, the diode conducts heavily. We can there is a standard equation for this, that is I equal to I naught e raised to EV by KT minus 1, where I is the diode current, I naught is the reverse saturation current, E is the charge of an electron, V is the applied voltage, K is the Boltzmann constant, K is the absolute temperature. This forward bias condition is used in rectifiers, like to convert AC current to DC current. Now let's see the PM junction. A PN junction is said to be reverse biased when the P type of the semiconductor is connected to the negative terminal of the battery and the N type of the semiconductor is connected to the positive terminal of the battery. Here it will be positive terminal, and here it will be negative terminal. In reverse bias, the external electric field supports the internal electric field of this junction, and holes are pulled here. Holes are pulled away from this junction, and electrons also pulled away from the junction. And what happens? This depletion region here, it becomes widened, and barrier potential here also becomes widened. Barrier potential also increases. So here effective barrier potential becomes VB plus V. As a result, this junction offers very high resistance. And majority charge here, majority carriers cannot cross the junction because of this, and only small current is, only small minority carriers contribute to the current. This small current is called reverse saturation current. So from this we can conclude that in forward bias reduces the depletion region and allows the majority charge carriers to conduct, while reverse bias increases this depletion region and restrict the current flow and create very small saturation current. And this unique property of forward and reverse bias in PN junction act as a fundamental component in electronics, which ranges from like if you take as an example in forward bias, LEDs are the great example we can use in forward bias. Like LEDs, light emitting diodes itself shows when it connected in my forward bias, it emits lights, and this property also usually rectifies, like it converts AC current into DC current. And this reverse bias of a PN junction, where you can use it is in solar cells, that is the conversion of energy. So that is light energy to electrical energy. In this process, this reverse bias of a PN junction is used, and this is also usually Zener diodes and average photodiodes, which are usually high-speed optical communications and 3G, 4G, 5G networks.